Welcome to this tutorial on the scale-up of microbial fermentation aeration. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. Scale-up of microbial fermenters involves the scale-up of the major functional elements of a fermenter, namely, the microbial transformation reaction, stirring and mixing, aeration, and temperature regulation. This tutorial focuses specifically on the scale-up of aeration in microbial fermenters. This tutorial addresses aeration scale-up strategies in microbial fermenters. In aerobic processes, air is supplied via a sparger to disperse bubbles into the broth, enabling oxygen transfer from the gas phase to the liquid. The objective of aeration is to maintain the dissolved oxygen concentration above a critical level, ensuring adequate oxygen supply for cellular metabolism and preventing oxygen limitation. In this tutorial, we also examine scale effects by focusing on the fundamental phenomena that govern the aeration process in microbial fermentations. Because oxygen has a very low solubility in fermentation media, the overall aeration rate is most often limited by oxygen transfer from the gas phase to the liquid phase, rather than by gas supply itself. Oxygen from the air phase dissolves at the gas-liquid interface and is subsequently transported to the microbial cells, where it is consumed for metabolic activity. The dissolved oxygen concentration in the fermenter is therefore determined by the dynamic balance between the rate of oxygen transfer from the gas phase and the rate of oxygen consumption by the cells. Fermentation processes are typically developed and optimized at laboratory scale, using fermenters with working volumes of only a few liters. These processes are then progressively scaled up through pilot units to industrial fermenters, whose working volumes may range from tens to several thousands of cubic meters. During fermentation scale-up, aeration is often the most challenging aspect, as it becomes increasingly difficult to transfer sufficient oxygen to the culture. Inadequate aeration can lead to oxygen limitation at industrial scale, with detrimental effects on microbial growth, metabolism, and process performance. In this tutorial, we address the following two key questions. How should the airflow rate be scaled up? What are the scale effects on the oxygen transfer process? Based on this analysis, we then propose practical guidelines for the scale-up of aeration systems in microbial fermenters. When scaling up aerobic fermentations, the airflow rate is a key operational variable, as it largely determines the oxygen supply available to the culture. Air is continuously introduced at the bottom of the fermenter, most commonly through a sparger, which disperses the gas into bubbles that rise through the liquid phase of the medium. The airflow rate QA is expressed in cubic meters per second or in liters per minute. The airflow rate serves two essential functions. It ensures the efficient dispersion of air throughout the fermenter, thereby limiting oxygen depletion within the rising gas bubbles. It generates a sufficiently large gas-liquid interfacial area, which is required for effective oxygen transfer from the gas phase to the liquid phase. For the design and scale-up of fermenter aeration systems, the most commonly used aeration criterion is the airflow rate per unit volume of liquid medium. The volumetric airflow rate is defined as the ratio of the inlet airflow rate QA to the liquid medium volume V. This parameter is commonly expressed in VVM, volumes of air per volume of liquid per minute. In aerobic fermentations, typical operating values of the volumetric airflow rate range from 0.5 to 2 VVM, depending on the organism, medium, and oxygen demand. The volumetric airflow rate characterizes the overall intensity of aeration throughout the fermentation medium. It directly influences the oxygen molar fraction in the outlet gas, and consequently, the mean oxygen partial pressure and oxygen solubility in the liquid phase. Inside the fermenter, the oxygen molar fraction in the gas phase decreases from its inlet value, YO2 in the supplied air, to a lower value, YO2 out, in the exhaust gas leaving the fermenter. The influence of the air volumetric flow rate on the oxygen molar fraction in the air phase through the fermenter is shown by the oxygen balance on the fermenter. In this balance, expressed in gram oxygen per minute or hour, the oxygen inlet rate is 32 Qa over V mol times YO2 in, where V mol is the air molar volume, 22.4 liters at 0 degrees Celsius and 1 atmosphere pressure. The oxygen consumption rate in the fermenter is the product of the volumetric oxygen consumption rate, RO2/3, by the medium volume V. The oxygen outlet rate is 32 Qa over V mol times YO2 out. Accordingly, for a given oxygen consumption rate, it is the volumetric airflow rate per unit liquid volume, Qa over V, that determines the remaining oxygen molar fraction in the exhaust gas. YO2 out equals YO2 in minus RO2/3 divided by 32 Qa over V divided by V mol. How does the outlet oxygen molar fraction YO2 out vary during a fermentation? During batch or fed batch fermentations used for the production of metabolites or proteins, the volumetric oxygen consumption rate, RO2/3, typically exhibits a characteristic time profile. It increases during the early stages of the process, reaches a maximum, and subsequently decreases as growth slows or substrate becomes limiting. As a direct consequence, the oxygen molar fraction at the outlet, YO2 out, correspondingly decreases at the beginning of the fermentation, reaches a minimum, and then increases again as the cellular oxygen demand declines. What is the influence of the volumetric airflow rate on this time evolution of YO2 out? For the metabolite fermentation illustrated here, with a maximum oxygen consumption rate of approximately 2 grams per liter hour, operation at a volumetric airflow rate, Qa over V of 1, results in an outlet oxygen molar fraction that remains close to the inlet value of 0.21. Reducing the volumetric airflow rate leads to a lower oxygen partial pressure in the outlet gas. The decrease in YO2 out is relatively modest when Qa over V is reduced from 1 to 0.5, but becomes much more pronounced when the airflow rate is further lowered to 0.2, reflecting a progressively tighter balance between oxygen supply and cellular oxygen demand. In addition to the volumetric airflow rate, the second aeration criteria to consider during scale-up is the gas superficial velocity. The gas superficial velocity, UG, is defined as the airflow rate, Qa, divided by the cross-sectional area of the fermenter, A. It is expressed in cubic meter per square meter per second, which is equivalent to meter per second, or sometimes meter per minute. The superficial gas velocity can be related to the previous volumetric flow rate criteria. UG is the product of the volumetric flow rate Qa over V by the medium height HM in the fermenter. The superficial gas velocity is an important parameter because air is not introduced uniformly throughout the entire liquid volume. Instead, it is injected at the bottom of the fermenter through a sparger that distributes gas over the cross-sectional area of the vessel. As a result, UG directly characterizes the intensity of gas injection and the upward gas flow within the fermenter. Typical orders of magnitude of the superficial gas velocity in aerobic fermentations are 0.005 to 0.02 meter per second for large-scale industrial fermenters. Increasing the airflow rate in aerated fermenters is often limited by the onset of air flooding or excessive foaming. Air flooding occurs when the sparge gas is no longer efficiently captured, broken up, and dispersed by the impeller. Instead, air accumulates below or around the impeller and rises directly through the vessel as large gas cavities or slugs. Under these conditions, the impeller becomes partially or fully gas-filled, resulting in a loss of effective contact with the liquid phase and a marked deterioration of mixing and oxygen transfer performance. Foaming occurs when gas bubbles rising through the fermentation broth do not readily collapse at the liquid surface, but are instead stabilized by surface-active compounds produced or released during the fermentation. This leads to the formation of a persistent foam layer in the headspace, which can cause operational difficulties and limit further increases in aeration rate. There are two main strategies for scaling up the airflow rate in aerated fermenters. 1. Scaling with constant volumetric airflow rate. In this approach, the inlet airflow rate, QA, is increased in direct proportion to the fermenter working volume. For example, scaling up the fermenter volume by a factor of 1,000 requires a 1,000-fold increase in QA, which results in an approximately 10-fold increase in the gas superficial velocity, UG. This approach maintains a similar oxygen partial pressure gradient between the gas inlet and outlet. Consequently, it preserves comparable mean oxygen solubility within the fermenter. However, scaling at constant volumetric airflow rate can generate excessive turbulences and increases the risk of air flooding and foaming. 2. Scaling with constant superficial gas velocity. In this strategy, the airflow rate QA is increased in proportion to the fermenter cross-sectional area A, so that the superficial gas velocity remains constant across scales. Under this criterion, a 1,000-fold increase in working volume typically requires only a 100-fold increase in airflow rate, corresponding to an effective 10-fold reduction in volumetric airflow, compared with constant QA over V scaling. This approach preserves bubble rise velocity, gas holdup, and general gas-liquid hydrodynamics. It also reduces the risk of air flooding and excessive foaming. However, it is less effective at supplying oxygen throughout the entire fermenter volume. In addition to scaling up the airflow rate that supplies oxygen to the fermenter, it is also essential to consider the scale-up of oxygen transfer from the gas phase to the liquid phase. Only a fraction of the oxygen entering the fermenter is actually transferred into the liquid medium. This oxygen transfer is governed by gas-liquid mass transfer phenomena, involving diffusion and convection at the gas-liquid interface. The volumetric oxygen transfer rate, JO2/3, in gram oxygen per liter an hour from the gas phase to the liquid medium is described by the classical mass transfer equation, JO2/3 equals KLA, O2 star mean minus O2L, where KLA in hour minus 1 is the volumetric oxygen transfer coefficient equal to the product of the liquid side mass transfer coefficient, KL, and the specific interfacial gas liquid area A. O2 star mean is the mean oxygen solubility concentration at the gas-liquid interface in the fermenter. O2L is the dissolved oxygen concentration in the bulk liquid phase. In this formulation, both the mean oxygen solubility, O2 star mean, and the volumetric mass transfer coefficient, KLA, are scale-dependent quantities. The rate of oxygen transfer in a fermenter depends on the mean oxygen solubility in the fermentation medium, which can vary with scale due to increased hydrostatic pressure. As fermenter volume increases, so does the height of the liquid column, leading to a greater pressure difference between the gas inlet at the bottom and the gas outlet at the top. This pressure difference is given by the hydrostatic relation, P in equals P out plus rho GHM, where P in is the inlet air pressure at the bottom, P out, the outlet air pressure at the top. Rho, the medium density, G, the gravitational acceleration, HM, the medium height. The mean oxygen partial pressure in the fermenter is determined as follows. At the air inlet, the oxygen partial pressure PO2N is the product of the inlet oxygen molar fraction YO2N by the inlet pressure P in. At the air outlet, the oxygen partial pressure PO2 out is the product of the outlet oxygen molar fraction YO2 out by the outlet pressure P out. The mean oxygen partial pressure in the bioreactor, PO2 mean, is calculated as the arithmetic average between the inlet and outlet oxygen partial pressures, and the mean oxygen solubility, O2 star mean, in gram per liter in the fermenter medium is calculated as the mean oxygen partial pressure divided by the Henry solubility constant KO2. Consequently, the mean oxygen solubility is scale-dependent, reflecting both the increase in hydrostatic pressure at the bottom of large fermenters and the decrease in oxygen molar fraction in the outlet gas. The volumetric oxygen transfer coefficient, KLA, is influenced by several operational and physical factors, including the airflow rate introduced into the fermenter, which affects gas holdup and bubble size distribution. The sparger design, such as drilled hole spargers or macroporous spargers, which determines the initial bubble size. The impeller stirring rate, which controls bubble breakup, dispersion, and liquid side mass transfer. The viscosity of the fermentation medium, which influences bubble rise velocity and liquid phase diffusivity. The surface tension of the medium, which affects bubble formation and stability. Fermentations that exhibit a strong increase in broth viscosity during the course of the process are among the most challenging systems to scale up. Viscosity typically increases as a result of biomass accumulation, exopolysaccharide production, and filamentous microbial morphology. An increase in viscosity during fermentation leads to a significant reduction in the volumetric oxygen transfer coefficient KLA. This reduction arises from the combined effects of a decrease in the liquid side mass transfer coefficient KL and a decrease in the gas-liquid interfacial area A, the latter being primarily caused by enhanced bubble coalescence and reduced bubble breakup. The volumetric oxygen transfer coefficient KLA is probably the most scale-dependent variable in aerobic fermentations. Its dependence on operating conditions is commonly described by empirical correlations of the form KLA equals K PAG over V power alpha, UG power beta, mu power gamma, where PAG over V is the agitation power per unit volume, UG is the superficial gas velocity, and mu the viscosity of the medium. According to this relationship, KLA is governed primarily by the energy input for agitation, the gas flow intensity, and the rheological properties of the broth. The coefficients K, alpha, beta, and gamma depend on the fermenter geometry, scale, impeller, and sparger design, as well as on the physical properties of the medium. As a result, precise prediction of KLA values in fermentation systems is difficult, particularly during scale-up. For low viscous fermentation media, the typical orders of magnitude of KLA are between 100 and 500 hour -1 in small laboratory fermenters, between 50 and 200 hour -1 in intermediate and large-scale fermenters. As a consequence, a substantial reduction in KLA is generally unavoidable when scaling up aerobic fermentations. What are the consequences of a reduced volumetric oxygen transfer coefficient on the time course of the dissolved oxygen concentration during a fermentation? The dissolved oxygen concentration in the liquid phase, O2L, results from the instantaneous oxygen balance on the liquid phase in the fermenter. At any given time, this balance expresses the equality between the oxygen transfer rate from the gas phase to the liquid and the oxygen consumption rate by the microbial cells. When expressed per unit volume of medium, this balance can be written as JO2 equals RO2. This relation is often expressed under the form oxygen transfer rate, OTR, equals oxygen uptake rate, OUR. When the volumetric oxygen transfer rate, JO2, is expressed as a function of its rate law, the equality between the oxygen transfer rate and the oxygen consumption rate writes KLA O2 star mean minus O2L equals RO2. Under these conditions, the dissolved oxygen concentration O2L is given by the relation O2L equals O2 star mean minus RO2 third over KLA. Thus, the dissolved oxygen concentration is equal to the mean oxygen solubility in the fermenter, reduced by the ratio of the volumetric oxygen consumption rate to the volumetric mass transfer coefficient. For batch or fed batch fermentations used for the production of metabolites or proteins, the volumetric oxygen consumption rate typically increases during the early stages of the process, reaches a maximum, and subsequently decreases. In order to maintain the balance between oxygen transfer and oxygen consumption, the dissolved oxygen concentration correspondingly decreases at the beginning of the fermentation, reaches a minimum, and then increases again as the cellular oxygen demand declines. What is the influence of the airflow rate on the time evolution of the dissolved oxygen concentration? The airflow rate through the fermenter exerts a dual influence on oxygen availability. It affects the mean oxygen partial pressure in the gas phase, and therefore the mean oxygen solubility in the fermenter. It influences the volumetric oxygen transfer coefficient, KLA. A decrease in the volumetric airflow rate, QA over V, leads to a lower mean oxygen partial pressure in the gas phase passing through the fermenter. As a consequence, the mean equilibrium oxygen solubility is reduced. In addition, a lower airflow rate generally results in a decrease in KLA, further reducing the oxygen transfer rate. The combined effect is a lower dissolved oxygen concentration during the course of the fermentation, thereby increasing the risk of oxygen limitation. The decrease in dissolved oxygen is relatively modest when QA over V is reduced from 1 to 0.5 VVM, but becomes much more pronounced when the airflow rate is further lowered to 0.2 VVM. What is the influence of scale on the dissolved oxygen concentration dynamics? Because both the mean oxygen solubility and the oxygen transfer coefficient vary with scale, the dynamics of the dissolved oxygen concentration inevitably change as fermenter size increases, even when operating under otherwise similar conditions. In general, oxygen supply and gas-liquid mass transfer are less efficient in large-scale fermenters than in small laboratory vessels. As a result, industrial-scale fermentations tend to operate at lower dissolved oxygen concentrations, increasing the risk of oxygen limitation. When the dissolved oxygen level falls below critical values, cell growth, metabolism, and product formation may be adversely affected. In the final part of this tutorial, building on the analysis of scale effects, we propose practical guidelines for the scale-up of aeration systems in microbial fermenters. When scaling up from laboratory to industrial fermenters, the objective is not to reproduce the dissolved oxygen dynamics observed at small scale, as this is generally impossible. Instead, the goal is to ensure that the dissolved oxygen concentration does not fall below a critical level, thereby preventing oxygen limitation throughout the process. This is achieved by selecting appropriate aeration conditions, in particular the airflow rate and the operating pressure, controlling the oxygen demand of the culture, mainly through regulation of the cellular biomass concentration. When scaling up aerobic fermentations from laboratory-scale fermenters to large-volume industrial vessels, the first and most critical step is the selection of an appropriate airflow rate. As discussed earlier, operating at a high volumetric airflow rate is generally advantageous because it helps maintain a high mean oxygen partial pressure in the gas phase, increases oxygen solubility in the liquid, and enhances oxygen transfer rates. Laboratory fermenters are commonly operated at volumetric airflow rates QA over V of approximately 0.5 to 1 VVM. An initial scale-up objective is therefore to operate large-scale fermenters at similar volumetric airflow rates. However, the maximum usable airflow rate must remain below the thresholds for gas flooding and excessive foaming, which depends strongly on the microorganism, medium composition, and fermentation phase. Consequently, the large-scale volumetric airflow rate must be tailored to the specific fermentation. In large-scale fermenters, oxygen solubility can be increased by operating the vessel under elevated pressure. This is typically achieved by increasing the headspace or outlet pressure. In industrial fermenters, the overhead pressure is commonly raised by approximately 0.1 to 1 atmosphere above atmospheric pressure. This increase in total pressure leads to a proportional increase in the oxygen partial pressure in the gas phase. As a result, the equilibrium dissolved oxygen concentration in the liquid phase increases, thereby increasing the mean oxygen solubility in the fermenter medium and improving the driving force for oxygen transfer. Because the volumetric oxygen transfer coefficient KLA generally decreases with scale, leading to lower dissolved oxygen concentrations, the recommended scale-up strategy is to adapt fermentation operation so as to avoid critically low dissolved oxygen levels that would result in oxygen limitation. To prevent oxygen limitation during fermenter scale-up, the following engineering guidelines can be formulated by controlling cellular activity throughout the fermentation. These guidelines rely on a quantitative evaluation of the maximum achievable oxygen transfer rate under the selected operating conditions at the target scale, the maximum oxygen consumption rate expected during the course of the fermentation, the maximum biomass concentration that can be safely attained without oxygen becoming limiting. The first step is to evaluate the maximum usable volumetric oxygen transfer rate, JO2/3 max. The volumetric oxygen transfer rate is given by JO2/3 equals KLA O2 star mean minus O2L. The oxygen transfer rate increases with the driving force, O2 star mean minus O2L, and would be maximal if the dissolved oxygen concentration were allowed to approach zero. In practice, however, the dissolved oxygen concentration cannot be reduced indefinitely as cells experience oxygen limitation below a critical threshold, O2L mini. Below this minimum dissolved oxygen concentration, cell growth rate decreases and undesired byproduct formation may be induced. Therefore, the maximum oxygen transfer rate that can be utilized without inducing oxygen limitation is given by JO2/3 max equals KLA O2 star mean minus O2L mini. The maximum volumetric oxygen transfer rate, JO2/3 max, is scale dependent. In large volume fermenters, the mean oxygen solubility is generally higher, mainly due to increased hydrostatic pressure. In contrast, the oxygen transfer coefficient KLA typically decreases with increasing scale. In practice, the reduction in KLA outweighs the increase in oxygen solubility. As a consequence, the maximum usable oxygen transfer rate is lower in large-scale industrial fermenters than in small laboratory-scale systems. To avoid oxygen limitation, the volumetric oxygen consumption rate must remain below the maximum usable oxygen transfer rate during the entire course of the fermentation. For batch or fed-batch fermentations used for the production of metabolites or proteins, the volumetric oxygen consumption rate increases during the early stages of the process, reaches a maximum, and subsequently decreases. Accordingly, the maximum allowable oxygen consumption rate, O2/3 max, is equal to the previously defined maximum oxygen transfer rate, JO2/3 max. Because large-scale fermenters generally exhibit a lower maximum usable oxygen transfer rate, they must be operated at a lower peak oxygen consumption rate to avoid oxygen-limiting conditions. From this maximum oxygen consumption rate, one can determine the maximum biomass concentration that can be attained without inducing oxygen limitation. The volumetric oxygen consumption rate, O2/3, is given by the product of the specific oxygen consumption rate, QO2, expressed in gram oxygen per gram biomass an hour, and the biomass concentration X. This specific oxygen consumption rate is related to the cell-specific growth rate, and/or the specific metabolite production rate, depending on the fermentation kinetics. Accordingly, the maximum biomass concentration X max that can be achieved without oxygen limitation is equal to the maximal volumetric oxygen consumption rate, RO 2/3 max, divided by the specific oxygen consumption rate, QO2. Because large-scale fermenters generally exhibit a lower maximum allowable oxygen consumption rate, they must be operated at a lower biomass concentration, at comparable QO2, to avoid oxygen-limiting conditions. As an illustration of aeration scale-up in a stirred fermenter, consider a cylindrical fermenter with a diameter of 4 meters, containing 100 cubic meters of culture medium, corresponding to a liquid height of approximately 8 meters. At an agitation power input of 1 kilowatt per cubic meter and a volumetric airflow rate of 0.5 VVM, the volumetric oxygen transfer coefficient is estimated to be approximately 150 hour minus 1. The fermenter is pressurized at an overhead pressure of 1.5 atmosphere. Under these conditions, the mean oxygen partial pressure in the fermenter is about 0.4 atmosphere, corresponding to a mean oxygen solubility of approximately 13 milligrams per liter. Assuming a minimum allowable dissolved oxygen concentration of 1 milligram per liter, the maximum usable volumetric oxygen transfer rate is around 1.8 grams of oxygen per liter an hour. For a microbial culture having a specific oxygen consumption rate, QO2, around 0.35 gram oxygen per gram biomass an hour, the maximum biomass concentration that can be sustained without oxygen limitation is estimated near 5 grams per liter. Let's further consider the example of fermentation scale-up with controlled biomass concentration to avoid oxygen limitation. A metabolite-producing fermentation is scaled up from a 10 liters laboratory fermenter operated at an overhead pressure of 1 atmosphere and characterized by a high volumetric oxygen transfer coefficient, KLA, approximately 500 hours to the minus 1, to an industrial fermenter of 100 cubic meters operated at an increased overhead pressure of 1.5 atmosphere, but exhibiting a significantly lower oxygen transfer capacity near 150 hour minus 1. At both scales, the biomass concentration is actively controlled to prevent the dissolved oxygen concentration from dropping below 1 milligram per liter, thereby avoiding oxygen-limited conditions. Under these constraints, the maximum attainable biomass concentration decreases from 7 grams per liter at laboratory scale to around 5 grams per liter at industrial scale. As a direct consequence, the final metabolite concentration, after 24 hours of fermentation, is reduced from 65 to 50 grams per liter. This example illustrates that scaling up a fermentation with a substantial reduction in KLA, even when partially compensated by increased operating pressure, can lead to lower allowable biomass concentrations and ultimately to reduced fermentation productivity. In summary, this tutorial has addressed the challenges and methodology associated with the scale-up of aeration in microbial fermentations. Aeration scale-up is inherently difficult because most key variables are strongly scale-dependent, including oxygen solubility, the volumetric oxygen transfer coefficient KLA, and the resulting dissolved oxygen dynamics during the course of the fermentation. The principal operational parameter governing aeration is the airflow rate through the fermenter, which determines both the oxygen content of the gas phase throughout the vessel and the gas-liquid interfacial area available for oxygen transfer. A practical guideline is therefore to operate at the highest feasible volumetric airflow rate, while remaining below the thresholds for air flooding and excessive foaming. Because oxygen transfer efficiency and dissolved oxygen levels are generally lower at large scale, oxygen limitation can be avoided by appropriately controlling the cell concentration and oxygen consumption rate, such that the maximum cellular oxygen demand remains compatible with the achievable oxygen solubility and transfer capacity of the industrial fermenter. If interested, you can gain a deeper insight in the scale-up of microbial fermentations by enrolling in the online courses, Digital Scale-Up and Optimization of Microbial Fermentations, or Simulation, Scale-Up and Optimization of Fermentation Processes. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.